of hydrogenation. Heat of hydrogenation. So what is heat of hydrogenation? That is amount of heat released when 1 mole of alkene undergo hydrogenation. When 1 mole of alkene undergoes the hydrogenation. So, like we have any alkene, and when it reacts with H2, the H2 will add on it and it will form CHCH. And delta H is less than 0. It is an exothermic reaction. Delta H heat releases in that particular reaction because alkane is less stable and alkane is more stable. So, it will lose the heat and the heat will release. So, let's say we have two cases A where that particular alkene react with and it form normal butane. When we have B, it will react with H2 when it is normal butane. Both are forming the same product, right? Now, when both are forming the same product, we have A and B, and both are, this is A and B, and this is a C. Both are forming C. So when the heat is released, when the heat is going like this, so when both are forming the same product, but in case of A, there is a change in delta HA. This particular heat is known as delta HA, and this particular heat is known as delta HB. Delta HA and delta HB. So we know as the magnitude delta HA is greater than delta HB. So delta H is inversely proportional to stability of alkene. Delta H is inversely proportional to stability of alkene. More will be the heat released, lesser will be the more the heat released, lesser will be the stability of alkene. Alkene. So heat of hydrogenation is inversely proportional to stability of alkene. You can learn from that B is more stable, so heat of hydrogenation is less. A is least stable, so heat of hydrogenation is more. So generally we compare when both are forming the same product, but still we can compare in other side also. So let's compare the stability, the heat of hydrogenation. So when we calculate the heat of hydrogenation, compare heat of hydrogenation. So first we have I am writing some questions. You have to just compare the heat of hydrogenation. Now in this part we have to compare heat of hydrogenation. In directly you have to compare the stability of alkene and count the number of alphides. Lesser the number of alphides, more will be the stability of alkene, more will be the heat of hydrogenation. And first and second, the heat of hydrogenation A is more. In that case, B is more. In that case, third case, we know that it has two double bond, and first case has two double bond, second case has one double bond. So heat of hydrogenation is indirectly proportional to number of sigma bonds. In fourth case, B is greater than A. In fifth case, one is aromatic, second is anti-aromatic. So in fourth case, it is resonance, and here is only hyperconjugation. So stability is less, right? Now if we compare some more questions, we have done 5 questions. Let's solve some more questions. We have a lot of questions in our sessions, so keep that in mind. That is our unique point. So sixth, seventh, CH2 double bond CH, CH2 CH3, CH2 double bond CH, CH CH3, and CH3. Eighth, we have ninth, we have 10th, we have 11th, we have this is known as anthracene. We are comparing its heat of hydrogenation with phenanthrene. Phenanthrene, anthracene and phenanthrene. So in sixth, we have first 1, 2, 3, 4, 4 alpha 1, 2, 3, 4, 5, 6. So this is when we more heat of hydrogenation. And in seventh, we have heat of hydrogenation more over here because stability alpha H here is less. In eighth case, it is anti-aromatic system, anti-aromatic, and in the non-aromatic system. So less stability, more heat of hydrogenation. Here we have resonance, and here we have mesomeric effect. So mesomeric effect will we have more. In case of here aromatic, we have means more resonance, and here we have hyperconjugation. So this will be the order of stability A, B, C. But But we have over here the heat of hydrogenation will be more in case of B, then C, then A. If it is A, B, and C, then we will be having B, then C, then A. The data you have to remember. It is our data that we have studied the resonance energy. The resonance energy we have studied, and we have seen the resonance energy in thermochemistry also. So since it has two double bonds, so it is 2x, it is x, it is 2x, and it is 3x. But in here, where resonance energy is less, resonance energy is less. Its resonance energy is high, its resonance energy is low. So overall data says us B, C, A. That is an experimental data. So you have to just remember the values, not values, the order. B, C, then A. Heat of hydrogenation order. Now let's talk about heat of combustion. Heat of combustion. So what is heat of combustion? We have CXHY plus X plus Y by 2 O2 forming XCO2 plus YH2O. Its delta H is less than 0. Heat is releasing. Heat is releasing. Delta H is less than 0. So if we have two compounds C4H8, C4H8. So in both the case C4H8 plus 6O2 forming 4CO2 plus 4H2O. If number of carbon is same, if we compare number of carbon is same, then heat of combustion is inversely proportional to stability. Heat of combustion is inversely proportional to the stability. Less than stable, more is the heat of combustion. Again, how? If number of carbon is same, if we give it as a A, and if you give it as a B name, so if I draw the curve, we know that B is more stable, A is less stable, and both are forming C, which is CO2. So it is forming like this, it is forming like this. It is delta HB and it is delta HA. So stability is inversely proportional to heat of combustion. You can easily see with the help of graph. Let's solve some heat of combustion problem. It is similar to heat of. We can only compare if number of carbon are same. But if number of carbon are different, that is directly proportional to the number of carbon. So in that particular case, alpha H we have 9. Here alpha H we have 5. So this is more heat of combustion. In second case, we have alpha H as 10. We have alpha H as 4. So this is more. In third case, we have now all the four have different number of carbon. So heat of combustion depends number of carbon. Obviously, when the number of carbon will be more CO2 will form, more heat will release. So when carbon are different, we will give it like this. In fourth case, here number of carbon are same, but when number of carbon are same, then stability. What is the order of stability? Cyclohexane. First of all, let's talk about the order of stability in cycloheptane, cyclohexane, cyclopentane, cyclobutane, and cyclopropane. So which has more stability? Cyclohexane has more stability than this. Because here we have angle strain. What is angle strain? Angle strain, like if in a triangle, the angle is like 60 degree. But according to SP3, it is 109 degree 28 minute. So angle strain is 109 degree 28 minute minus 60 degree. So it is 49 degree 28 minute. So that much angle strain, that much less angle it has, right? And it has 90 degree 109 degree 28 minutes minus 90 degree 19 degree 28 minute, right? And the angle is keep on decreasing, right? Angle is keep on, the angle strain means the angle should be like 109 degree 28 minute, but it is reduced to 60 degree. So there is a lot of strain we have here. Lesser strain 109 degree, but it is 90 degree. So angle has to means it has to be like this, but we have compressed it like this. So more the compression, less will be the, but the compression is very minimum in case of cyclohexane. We will see that in isomerism. So if number of carbon are same, the stability is lesser here. So heat of combustion, the order will be like this. Now let's draw some two more questions. So heat of combustion in 1, 2 and 3. This will be the order. And here 1, 2, 3. Obviously inversely proportional to the stability of alkane. And stability of alkane is inversely proportional to the number of alpha H. The number of alpha H. Stability of alkane is directly proportional to number of alpha H. And heat of combustion is inversely proportional to stability. So stability is inversely proportional to number of alpha H.